Hi there, and thanks for joining me and my lecture regarding magnifying glasses. So in a way, this is a kind of bridging lecture between the human eye. We just previously discovered how it behaves, and then our final lectures regarding the eyepiece, the ocular, and then the microscopes and telescopes. So essentially how we can start making optical instrumentation by just putting things together. So in a way, the magnifying glass is the kind of simplest possible scenario of understanding how we can form magnified images, and then it acts in a way as a motivation towards microscopes, optical microscopes. So we will basically now in the lecture learn how a simple positive lens could be used to magnify an object into a magnified image that are then being seen at our human eye, and then we can either play around or we can actually take that for benefit and for something useful. And let's look more carefully of this problem at hand, because this is essentially what limits the resolution of the human visual perception, as has been highlighted in the figure, and we somehow want to understand how we can improve the resolution so that how we can look at smaller objects at the same human eye, and then this teaches us something about the near point of our human eye and how the human vision works, and of course also acts as a motivation towards the follow-up lectures. So let's look at the kind of a size of my image that is being formed of an object described in the A figure. So I have my objects, and the size of the object is denoted with the y0. That's the distance from the object point from the optical axis. And now the image is being formed into the retina of my eye, and yi describes the size of my image. And basically, what is the size of my image yi depends on the viewing angle. And this is the concept that we are using to understand how a magnifying glass works, and rather not just a kind of transverse magnification, but rather we go slight on a detour and look at the viewing angles and how we can adjust that. And now we of course know that if you want to increase things, we can bring the object closer so that the transverse magnification can be increased. But then the trouble is that we can only go as close as to the near point of our human eye, and that is denoted with the D0, DO in the figure. And this is the kind of restricting parameter that restricts the kind of maximum magnification all of our eyes can get. We cannot anymore focus into a point that is closer to the near point, and then that limits the kind of maximum transverse magnification I have with my eye. And the kind of viewing angle that we can get, the kind of largest viewing angle roughly will be the ratio of y0 divided by the d0. So that basically I can take the tangent of this angle here, the viewing angle, and since do is quite large compared to the size of my sample, well, I want to look by definition with the magnifying glass something that is small, so the yo will be small. And then I can take the tangent, and the tangent is roughly the angle in itself. Because the angle is small, I can write this kind of equality. And of course, it's approximately true because we are approximating the tangent of alpha to be alpha in itself. But this is a fine approximation in this case of our interest. And when we are using a magnifying glass, so essentially a lens that has a positive focal length, the situation can be increased, improved, and this is essentially shown in the B figure. So here what we do is that now the object can be brought closer to the eye, and this essentially increases the viewing angle that we have. And this has been shown in the B figure so that we can increase the kind of new viewing figure alpha A essentially by just using a positive lens between the object and our eye. And this helps because essentially now our object is forming a virtual image. The lens is forming a virtual image of our object, ideally at the infinity. And then when our eye is forming an image of our object point that is infinitely far away here, then it seems that it's actually coming, the bunch of rays that are coming and forming the image through our eye, these are actually coming from an angle that is larger, and thus the image will be larger. So, ideally, a magnifying glass, like I already mentioned, forms a virtual image of my object point infinitely far away from the eye, and the point is that the viewing angle will be increased. And looking at the geometry of the B figure, we can see that the new viewing angle alpha A, it's essentially the sine of alpha A, and then this is essentially YO divided by F. So looking at the triangle here, I can look at the ray propagating along the optical axis. It's hitting the principal plane of my lens, and then it's being at the given angle through the system. So that this angle here that it makes, it's roughly the ratio. It's roughly alpha. It's for small angles. It's roughly sine of alpha, and the sine of alpha can be defined that it's essentially here. Looking at here, it's the YO divided by F. So that that's how we can get into the things. And now we can define the magnification. This is like essentially the transverse magnification of my system. The magnifying power in some communities, it's not being called transverse magnification when we're looking at magnifying glasses, but rather magnification power. Then this is defined as the ratio of the viewing angles, so that if you can increase the viewing angle alpha A with respect to the original viewing angle, then we have a magnified image. And then this, as written, can be written to be that it's the dO over F. And essentially, if you write the 1 over F as the lens power D, we can see that if we increase the power of the lens, we can increase the magnifying power. And of course, if we would be being able to adjust the location of my object, the transverse magnification will be changed accordingly. An example calculation would be that if I would have a magnifying glass that has a focal length of 10 centimeters, that would be 10 diopters in the optical units, then this kind of magnifying glass would result in a 2.5 magnification if the D node would be 25 centimeters. That's the near point location from the human eye. So this already shows us that even a somewhat moderate focal length then gives a kind of clear magnification of things. And of course, we could have a shorter focal lengths, and they would give a slightly better magnification. The trouble here of using just a single lens to magnify an object, to have a magnified image being formed, the trouble is that if you want to go into larger magnifications, the lens aberrations start kicking in, and they really start restricting the performance of my magnifying lens. So this is the kind of main message here. And the trouble is that basically, if you want to make a large magnifying glass, and this is usually the case, then the curvature of your spherical surface, ideally it will be spherical, then that will start considering giving you a spherical aberrations. And of course, you could have a non-spherical magnifying glass, but polishing that kind of glasses are not as easy anymore as making spherical surfaces, so that then in practice, it's most of the time not like a cost effective to make a magnifying glass that would have a higher lens power and thus a greater magnification. So that this is something. Of course, you could do a little bit of lens bending so that you could also change the other curvature, but nevertheless, like in practice, the magnifying glasses do have their limitations. We have few, of course, like in a family of a person teaching optics, we have a few magnifying glasses around, and there are clear differences. So definitely there are good ones and not so good ones. But nevertheless, like if you really want to go and see some very small objects, I recommend you to buy a microscope. You don't need to buy and invest on a very, very expensive microscope, but you can even get a pretty cheap one, a toy microscope with already a few tens of euros. And if you invest more, you can get actually quite good quality microscopes, and they would not be as restricting in terms of the lens aberrations, because there the objective lenses actually are being used or are being formed by using several lenses. So this is how things would go and progress in practice. But now I'm at the end of my lecture. I hope you enjoyed my prelude. And next, I will use this as a kind of motivation to go along a few lectures towards of understanding how an optical microscope works. And that is the kind of motivation of one motivation of this lecture. But I thank you for your patience, and I hope you enjoyed and I got the main message that the lens aberrations are actually important, and at some point they start limiting things. so that in soon you will actually progress to courses where we will be also discussing them more seriously, because they're actually quite big thing when we are looking at optical instrumentation and optics in general. But I thank you for your time and patience, and please join me shortly when I will be speaking about IPs known as the ocular. So thanks and bye-bye.